Let's do some practice problems on optimization. The follow along type of video. There's going to be 4 problems, I believe. Okay, so problem number 1, a farmer is preparing to breed cows. If the farmer sets up a rectangular pasture that is bordered on one side by a river, which requires no fence, what is the maximum area he can enclose with 1,000 feet of fence? So go ahead and try this first on your own. And then if you're totally stuck, let's observe how I'm thinking through the problems and setting up. Maybe you can mimic it. Okay. And then if you have an idea, you can of course check your answer. And then if you got something wrong, you can cross-check with how I did it. All right. So hopefully you tried it. So the whole idea of this is we're trying to maximize or minimize something, make something the biggest or make something the smallest. So what are we maximizing here? We're maximizing area of this rectangular pasture. Okay, so we got to set up an equation for this area. It's rectangular, so we call one of the dimensions x, one of the dimensions y. The area is just x times y. It's a rectangle. Okay, so we want to maximize this guy. How do we do that? We would need to take the derivative. Okay, and then this is where you learned about the max min, relative max min, and all that in the previous sections before you learned about these optimization word problems, or you worked on these optimization word problems. You learned about doing the first derivative test to determine if it's max min and all that. Okay, so that's why we need to differentiate this, set it equal to 0, and then solve for the critical points and all that. But the problem is this is a function of 2 variables. This function of area is a function of both x and y. In this course, you only know how to differentiate with respect to one variable. So we got to change this function of 2 variables into a function of 1 variable. Okay, this is how I always explain these problems to my students. Okay, so we need to find another equation to relate y and x such that we can change this equation of a into just x or just y. It doesn't matter which one. Okay, so how can we do that? Some books or some teachers call this, you need to find a constraint. How I learned it is this is the primary equation where we're trying to optimize the area, and we need a secondary equation precisely to get this into a function of 1 variable. So how can we get another equation? Well, we're going to use this other piece of information, 1,000 feet of fence. This is related to the perimeter, except it's not a fully enclosed rectangular pasture because it says that one of the sides is bordered by the river, so we don't need a fence. Well, we don't need fencing there. So if we call this dimension y, okay, and this dimension x, the perimeter or the amount of fencing that we have is y plus x. Okay, so turning that to equation, 1,000 equals 2y plus x. Okay, so we can either solve for y or x here. I guess I chose to solve for x here. So x equals 1,000 minus 2y. Okay, now we're going to plug this definition of x back into our a. Okay, so it would be now an equation of 1 variable, just y. So 1,000 minus 2y times y. Now we differentiate and set it equal to 0 to maximize it. A prime equals, you can distribute this to both terms, by the way. So the derivative would be 1,000 minus 4y equals 0. We solve for y. Y is 250. Here, I didn't check that this is actually, that a max actually occurs at y equals 250. We could check, but usually if you did it right, to be honest, you don't need to. And the question didn't ask for it, but you would have to do the sign test, the first derivative test. So I won't go over that yet. Let's hope that we did it right, which I did because I checked it. Okay. So y equals 250, but we got to answer our question. It's asking about the maximum area this farmer can enclose. So this is, you got to be careful in the multiple choice. One of the choices might be 250, but you totally didn't answer the question. It's asking for area, not dimension of this guy over here. So we got to plug it back into our A. Okay, since A is the area, and we found what Y is, so we plug it back in, you should get 125,000 feet squared. If this is a free response question, don't forget your unit of feet squared. Okay, and if it's a multiple choice, be careful to answer the actual question. So it's 125,000 feet squared. Right? So again, the idea is you need an equation of what you're trying to maximize. A lot of the times in these problems, it's a function of two variables. So you need to get it down to a function of one variable by a secondary equation or a constraint. All right. Hopefully that kind of made sense and how I thought through it. So number 2, calculator is for sure required for this one. What point or points on the graph of y equals cotangent x is closest to the coordinate pair pi comma 0? So go ahead and try this one. Okay, so what are we trying to maximize or minimize? It's asking for closest. So we're trying to minimize distance. Okay, we got to be thinking like that. So we need a formula for distance. We can use the distance formula, which is the Pythagorean theorem. Okay, so this is what I did. D squared, distance squared, is x minus pi quantity squared plus y minus 0 quantity squared. Okay, this is the distance formula right here with the distance from this coordinate point pi comma 0. Okay, so again, you can see this is an equation. This function d is an equation of two variables, x and y. We got to have a secondary equation to reduce it down to one variable. How do we do that? Well, y equals cotangent x. Okay, we can replace that right there. Okay, so we will get x minus pi quantity squared plus cotangent squared x. Now we can differentiate, set it equal to 0, find the critical point. So this is why I chose d squared instead of d equals square root of, and then that stuff, because it's nicer to differentiate. So 2d prime equals power rule and chain rule just times 1. Here you need chain rule, so 2 cotangent x times derivative of cotangent, which is negative cosecant squared, okay? So start solving for x. We set it equal to 0. Or I guess I divide by 2 first, and then I set it equal to 0. So then here's where we need to use the calculator. We graph this, see where it's 0, okay? I don't know if it got cut off on the screen share, but that's what I'm saying here. Graph it and look where it's crossing the x-axis. There's going to be a lot of points. So which ones do we pick? We want the ones closest to pi, x equals pi, closest. So we just pick the nearest ones, which looks like pi is 3.14, around there, right? So x is 2.163 and x is 4.12. You can see, by the way, since I have the graph here, it will be a minimum because the derivative went from negative to positive, which means the function decreased, then increased. So it's a relative min at both these points. Okay? That's what I was saying in the other problem. We check by the first derivative test. We check the sign. It went from negative to positive, so it's a min there. Relative min. Okay? So we pick these 2 points, and then we go and check the distance. When we do that, again, you need to calculate, you'll find that the distance is actually the same from these 2 points. Therefore, again, we got to answer the question. It's asking for the points, not just asking for the x values. They want the coordinate points, so both the x and y coordinates. So we got to plug into the calculator, and you should get these 2 points over here. Okay, so the hard part for this was, first of all, what are we trying to minimize? The distance. So we use the distance formula. And then here, there's many points. Which ones do we choose? Well, I want to choose where x is close to pi, because closest to this point. So I only chose those 2. Those are the closest, and then found the distance were the same, actually. Okay. Oh, this is the same thing. I guess I reformatted my stuff a bit. Okay, so let me delete that slide. Number 3. Find the, actually, I might reformat it again, so let me keep that. Okay, sorry about that. Problem 3. Find the maximum area of a rectangle that has 2 vertices on the x-axis and 2 vertices on the graph y equals x squared minus 8. All right, so go ahead and try this one. Okay, so it might be a good idea to sketch what's going on. Something like this. We know how this graph looks, x squared, but shifted down by 8, so something like that. We might not care about the 0, so don't even bother marking it. And then we can quickly find it. It's actually plus or minus square root 8, right? But we might not need it, so let's hold off on that. Okay, so what are we trying to maximize? The area of this rectangle. So how can we write an equation for that? Well, if this point is x comma 0, then just by symmetry, this one will be minus x comma 0. So the base or the width is 2x. Okay, and we call the height y, let's say. Okay, and nice, coincidentally or conveniently, maybe not a coincidence, y, because it's a function of two variables, y is our function, the parabola. Y equals x squared minus 8. So we can change this equation of two variables into one variable just by that, okay? And by the way, y is negative. The y value will be negative here, but we can't have a negative area, right? So we just tack on a negative sign as well. Again, the y coordinate at these points is under the x-axis, right? So it'll be negative. So we can't have a negative area. So we tack on another negative, so that will become positive. Okay, so we want to maximize this. So we differentiate. We just need the parabola. If we distribute those two terms, or just those two terms, set equal to 0. Solve for x. X should be, if I did it correctly, plus or minus, I believe I checked this, plus or minus 4 over square root of 6. Honestly, don't bother rationalizing this. Just leave it. Okay, you can rationalize it later if we really need to. And by this point, it's probably calculator problem, so it'll be a decimal value. Okay, we can just pick the positive. Okay. And now, therefore, the area, we got to remember, answer the question. Maximum area is, we plug it in, it would be 17.4186. Okay, so hopefully you see the pattern. We want an equation of the thing we're trying to maximize or minimize, in this case, the area, and we need a secondary equation if this guy is a function of two variables, which in these problems it usually is. Okay, and then after that, we differentiate it. Set it equal to 0, find a critical point, and then go answer the actual question. All right, last one. A 4-inch tall jewelry box will have rectangular sides and an open top. The longest sides of the box will be made of gold at a cost of $300 per inch squared. The shortest sides will be made of platinum at a cost of $550 per inch squared. The bottom will be made of plywood at a cost of 2 cents per inch squared. Square inches. What dimensions provide the lowest cost if the box has a volume of 50 inches cubed? Lots of information here, so try to dissect it and solve the problem on your own first. Okay, so what are we trying to maximize or minimize? Lowest cost. We're trying to minimize costs. We need an equation or a function for the cost of this box. Okay. And you can probably guess right now that our secondary equation or constraint to get it down to an equation of one variable will have to do with this volume of 50 inches cubed. Okay. All these have to do with the cost, and then this is probably the secondary equation. Okay. Just as you do more and more problems, you can probably guess right away from the pieces of information given. Okay. So sketch what's going on. Something like this, open top, okay? And the bottom was the plywood, okay? So, and then we have two sides of gold and two sides of plywood. Oh, no, wood's on the bottom, platinum is on two of the other sides, okay? So let's get an equation of the cost of this box, okay? So let's do the bottom first, the plywood one. It costs $0.02 or 2 cents per inch squared. So the cost would be 0.02 times the area. What's the area? It's just x times y, if we call it x and y, okay? Now for the two platinum sides, it tells us the 4-inch tall jewelry box, so the height is 4, okay? What's the cost? It is 550 times the area, which is y times 4. But there's two of them, so times 2 as well. Okay, that's what went on right there. Okay, and then that's the last term over here. And then the gold is 4 times x times that's the area times the cost, which is 300. Okay, and then times 2 because it's 2 of the bases. So this is the equation of the cost, and we can simplify like this, okay? And as I was saying, we're going to use the volume as our secondary equation. So how do we get the volume of this box? Length times width times height, or area of the base times the height, if you remember that general formula for prisms and cylinders, okay? So area of the base is x times y times the height, which is 4. So 4xy is 50. They give us that. So we can rewrite, or we can write it as x equals 25 over 2y. Can we simplify? And now we plug this into our cost function. Now, if we do the math and simplify, you should get this over here. I'm not going to go through all the steps, okay? Now, what do? We differentiate. So this is the equation, and once again, we differentiate. So this should be c prime, by the way. Okay, differentiate, set it equal to 0. We solve for y. So y equals 2.6112 inches. Okay, what was the question? What dimensions provide the lowest cost? So we need all the dimensions. So we found this dimension, y. We already know this dimension, 4. So we need this dimension, x. How do we get that? Well, we can use either the cost function again, or we can use this volume constraint. It doesn't matter. Okay. I would just use that volume constraint. So it's simpler to not plug in as many things to calculate, so that you would get x is equal to 4.7871. So the dimensions of the box are 4.787 inches by 2.6112 inches by 4 inches. Okay. All right, that's it for this problem set. Hopefully this was helpful to see how I think through the problems if you totally stuck. Okay, for these, you really cannot follow a set procedure because they can ask, like, what do? We had a maximizing or minimizing cost, which is related to the surface area. This one was maximizing area. This was minimizing distance. They can ask a lot of different things. This is maximizing area. They can do pretty much maximize or minimize anything. And you cannot memorize all possible cases because they can really ask anything. So you got to be able to reason through these problems. And how do we do it? Once again, primary equation, the thing we're trying to maximize or minimize. Secondary equation, if we need it to change this primary equation into a function of one variable, differentiate it, set equal to 0, find the critical points, and then answer the question. That's the general procedure to follow. All right. Hopefully, I'll see you in another video as well. Please give this video a like if it has helped you in any way, by the way. Thanks. Bye.